In the last module, we discussed equivalence classes. Using equivalence classes and partitions, we can study what the rational numbers are more precisely. So, this particular module will be intentionally a bit sketchy, but the details are not too hard. So, we have the set Q, which is supposed to be the collection of all ordered pairs. M comma n coming from the integers and n is not 0. As we saw in the last module, there is a difficulty. Several different elements in this set are actually identical. So what we do is instead we consider a new set. And the new set is, which again by abuse of notation I just denote by Q again, I just define it to be equivalence classes under tilde on Q. And what is tilde? Tilde is M comma n is related to P comma Q if and only if MQ is equal to NP. Okay. So I have put a equivalence relation on Q from tilde. We saw this equivalence relation in the last module. Now I consider the collection of all equivalence classes and I declare a rational number to be an equivalence class. So what needs to be done now is to equip this collection of equivalence classes with an addition and a multiplication. And how you do it is with what is known as a representative. So given any equivalence class, let's say A in Q, it can be represented as square bracket of M comma n, where M comma n is some ordered pair of integers with n not equal to 0. What I do is if I take two such equivalence classes, I am going to define what addition is. The addition is just defined to be equal to MQ plus NP comma NQ, the ordered pair given like this. Okay. Now if you have been observant, all I have done is taken LCM and done the addition in the rational numbers as we have learnt in middle school. The only issue that arises is that this equivalence class can be represented by any particular member of that equivalence class. That means I could have represented this M comma n as 2m comma 2n. Nothing is stopping me from doing that, right? And I could have represented this PQ as 3p comma 3q. Nothing is stopping me from that, right? Both are exactly the same equivalence classes. This means that the right hand side that I have written a particular equivalence class that should not change if I change the particular choice of representatives for the equivalence class Mn and the equivalence class Pq. If I had chosen a different representative, I should still get the same answer. Now that's not really difficult. You all know that it doesn't really matter which choice, how I represent the rational number, you get the same answer, but that needs a check, but it's just basic computation. Similarly, I can define M comma n multiplied by P comma Q as just MP comma NQ. This is just the standard multiplication formula in the rationals. Again, there is a check to be done irrespective of the choice of representatives of both equivalence classes. You must always get the same answer. That needs to be checked. And that's an easy check that can be done simply through basic arithmetic. So once these checks are done, you can check that all the familiar properties that rational numbers are supposed to have are indeed possessed by our collection of equivalence classes. You have to check things like associativity of addition, commutativity of addition, associativity and commutativity of multiplication, so on and so forth. What you precisely need to check is that the set Q as a structure known as a structure of a field. We will see more about fields in next week's modules. So this is the representation of Q as a collection of equivalence classes. There are some checks that you need to do. They are not really hard. I urge you to do them. This is a course on real analysis, and you have just watched the module entitled What are the rational numbers? Thank you.